Hey guys, it's me, Miss Miller, here to start Chapter 8. Today we're going to focus on linear equations with systems and also nonlinear equation systems. Linear equation systems should be very familiar from Algebra 1, and we've actually done some already at the beginning of the year, solving equations and such. Your nonlinear is what's going to be kind of new and applying that old information. So let's get started. When we're talking about linear equations and their solutions, there are three possible answers. If you look at two lines, they can intersect at one point. If they intersect at one point, we call that one solution. It's a consistent equation, an independent solution. Some of this vocab might be coming back to you. If you have two lines that are right on top of each other, meaning that every single point they have in common. And when that happens, it's a consistent equation still. The solutions are dependent on each other because you have infinitely many solutions. And then we have inconsistent equations when your lines are parallel and there's no solution. And so we'll kind of see what that looks like and how to solve. Finding that point is normally our goal. And if they are the same line, we write infinitely many. And if there is no point of I can't speak. If there's no point of intersection, then we say no solution. So there's two different methods. We're going to look at substitution and elimination with linear systems. A lot of times you're not asked specifically to do one or the other, but sometimes one's better than the other. So if we take a look, since we have a variable single by itself and an expression, that signals to me I need to do substitution, not just by the directions. So if you're ever not told how to solve, look to see if you have a variable solved for. So since I have what x is solved for, I'm going to take that and plug it in. So then I will have, I'm going to write over to the side here, 5x, whoops, we change that 5 times 2y minus 3 minus 4y equaling 9. And now you have one variable solved for, so we'll go ahead and do that. So I have 10y minus 15 minus 4y is 9. Combine like terms, and I get 6y minus 15 equals 9. Add your 15 over. When I add 15 to 9, I get 24. Divide by 6, and I get y is 4. Now, we are not done with the problem. Because I got a value for y, that means that this is not a no solution or infinitely many, that this is a, we have a solution, so I want to find also the x value. Now it's your choice. You can plug it into either equation, it doesn't matter. Plugging it into the second one's probably going to be my best bet. So I get x equals 2, and I'll substitute this back in. Hopefully this is just, a memory recall for us as I go ahead. And we always want to write our solution as a point. So my x is 5 and my y is 4. And I'm done. Another method is elimination. Now, obviously the directions here say elimination, but also by the setup I can tell. My x and y's are the same power value. They have the same degree. They're lined up. And so this will probably be easier for me to solve by elimination than it would be substitution. There's nothing stopping me, but I know how much we love fractions, so let's go ahead and solve this. Now, it's your choice. I like to do the addition method where we get opposite coefficients. So whether you want to get rid of x or y, it doesn't matter. Since y already has a positive and a negative, I'm going to multiply this equation so that we have common coefficients. So I want 8, so I'm going to multiply this by 4. And we do it to each term. It's always that end problem, the end term, what it's equal to, where a lot of us forget. So we want to make sure that we do that. So as we go ahead, we will get 12x plus 8y equals 192. And then this will stay the same. So I get 9x minus 8y equals negative 24. And by elimination, I can just add these equations together. So I end up with 21x. My y's will eliminate the whole point of this. And 192 minus 24 is going to give us 168. Divide that by 21. And x will be positive 8. So again, because we got an answer, we know we have a solution to find. It's not the end of this. So I want to go ahead and find y. It is up to you which one you want to plug into. I'm going to take my first equation. Something that I find is helpful for a lot of students is to rewrite it as to not confuse. A lot of times I'll see students write 3x and then minus 8y equals 48, just working too quickly, and we'll plug that 8 back in. So we have 3 times 8 plus 2y equals 48. 8 times 3 is 24 plus 2y equals 48. Subtract 24. So 2y equals 24. Divide by 2. And y equals 12. It's really important that my final answer is written as a point. Bada bing, bada boom, we're done. All right, so that was our quick little review for systems of linear equations. If you have any questions, feel free to reach out to me. Now, what's different with nonlinear systems, now we're into 8.4. I'm kind of jumping around, just makes more sense this way. Nonlinear systems, we've done a lot of nonlinear functions. We spent a whole unit on different parent functions. So one of those being, if we have a circle, remember circle, that parent function, or when we completed the square equals your radius squared, just so you have an idea, remembering that. And our parabola y equals, and we have ax squared plus bx. Let's see, any parabola. But if I were to ask you how many times does a parabola intersect a circle, what are the possibilities? Well, we could have one where the vertex is on the circumference of the circle. You could also have 2 where the vertex is on the inside of the circle and it's just crossing twice. You could have 3 where the vertex is on the outer rim of the circle but also is on the inside, inscribed in the circle. We could have a parabola where it is on the outside of the circle, so it's actually connecting 4 times. And then it's possible to just have no solution. So it's not as simple as with linear systems where I know if I get one y value, I have 1 point. If you get a y value, for instance, if we look here, the y value of 1 actually has 2 x values as its answer. And so we want to make sure that you're finding all the points and being extra careful. Other options between a parabola and a circle could be a parabola and a line. Obviously, there's possibilities for no solutions where they never intersect. You could have one solution where it's just tangent, it touches and then continues on, but it can also cross twice. So again, you want to be extra careful with your work, making sure you're finding those points. So I thought showing a visual might be helpful. Now, algebraically. So I said solve by substitution. For this, there would be no possibility of doing elimination. Well, that's not true because you do have y. But it wouldn't be the best bet because you would need to move over y, multiply, you get rid of y, and then have to solve a quadratic. Whereas here, we could get one of the variables alone and solve for it. So let's do what the directions say and solve by substitution. And I put the steps over here to the side. Since this is a little bit new for you, might be helpful, just kind of remember what to do. So we're going to solve one equation for the variable. Even though it's solved for x squared, I can't plug that in for x because that's not the same variable. They're not like terms. So obviously they're not the same variable. So we can't do that. But what I can do is solve for y. So if I take this second equation and I solve for y. So I can subtract 3x, so I'll get negative y equals negative 3x plus 9. And I'm going to divide by negative 1. Remember to do that to each term. Your accuracy is really important here, that we are extra careful in what we're doing. So we've done step 1. Now I'm going to take that and substitute it into my other equation. That's step 2. So now I'll have x squared equals 2 times 3x minus 9 plus 10. And what we're going to go ahead and do is distribute. So I get x squared equals 6x minus 18 plus 10. We'll clean this up a little bit. And notice I end up with a quadratic, 6x minus 8. Now, we know with quadratics, I can't just combine the x squared and the 6x. I have to get it to equal to 0, and we have 3 options. Those 3 options are factor it, quadratic formula, and complete the square. It is up to you with what method you want to do. I can already recognize this is factorable, so I'm going to move everything to one side, leaving my ax squared positive. And we will factor this. Factors of positive 8 that add up to negative 6 or negative 4 and 2. It's nice that a is 1. So I have x minus 4, x minus 2. I told you your favorite F word is going to be factoring. And I get that x equals 4 and x equals 2. So right there, I know I have a minimum of at least 2 points. And if you took a look from the beginning, I should have addressed this at the start, that this is a parabola and this is a line. We saw from this image that our choices are either 1 solution, 2 solution, or no solutions. So by getting 2 x values, I know I have 2 solutions to find. So now I can plug in. As long as I did this correctly, I can plug in. So I get y equals 3 times 4 minus 9. Y equals 12 minus 9. So y equals 3. And then I'll do the same thing here. Y equals 3 times 2 minus 9. So I get y equals 6 minus 9. So y equals negative 3. So my solutions, it's really important to organize your work in some way to make sure you're not switching around. I've seen this too many times where all this beautiful work is done, but then someone writes 4 and negative 3, 2 and positive 3, keeping in mind that when you plugged in 4, you got 3. So my solutions are 4, 3 and 2, negative 3. We have 2 solutions. Wouldn't it be great to see what this looked like on a graph, to see where those 2 points are intersections? I thought so too. So here we go. Here is our beautiful parabola that we were asked in the beginning. That first equation, here's my second equation, and these are our points of intersection. It worked out that they became perfect integers, but if it wasn't, we would write the exact value. If it's a fraction or square root, we want to keep our points, our solutions exact. All right, let's see another example, not one more. Here we have a line, x minus y equals 3. And then if you remember from earlier in the year, x minus 2 parentheses squared plus y plus 3 parentheses squared equaling 4. This is a circle where the center would be at 2, negative 3. The radius would be 2 because we take the square root. So we have a circle and a line. If you think about the different options, you could have a circle and a line where they never intersect, a circle and a line where it's just tangent at one point, and you could have a circle and a line intersecting at, I should probably draw this circle a little bit bigger, guys. Hold on, bear with me. Circle and line and 2 points. Sometimes that's helpful to just know a visual of what are your possibilities, just like I showed you with the parabola and a circle, that you could have up to 4 solutions. So if all of a sudden you got 5, you know that that's not going to work. So again, we're going to follow our steps. Solve an equation for one variable. I'm not going to touch the circle equation because it's going to be difficult, especially with taking the square root. We'll end up with pluses and minuses. It gets a little bit trickier. So instead, let's take our simpler equation, our linear equation, and solve for a variable. It does not matter what variable to solve for, but since we like to do things in the positive realm, if I just add y over, my rewritten equation would just be x equals y plus 3. I'm never trying to make the work harder. So now I can take that expression and plug it in for x. So again, accuracy is really important here. I have y plus 3 going in for x. Then minus 2, don't forget it, squared plus y plus 3 squared equals 4. Notice that our equation is now down to just one variable, all y's, and that's what we're going to solve for. Let's clean this up. I have y plus 1 squared plus y plus 3 squared equals 4. And now, where our algebraic skills are going to come really in handy is we're going to expand each of these. These are both perfect square trinomials. So if you remember that pattern, it's going to be y squared plus 2y plus 1, right? And then I am going to add y squared plus 6y plus 9 equals 4. If you forgot that pattern, remember you could just multiply it out. You could just do y plus 1 times y plus 1, and you'd FOIL, and you get y squared plus y plus y plus 1, which gives us y squared plus 2y. It gives us that same answer. But again, if you remember the patterns I've taught you, it kind of makes this go quicker. Now we can combine like terms. When we're dealing with quadratics, we want it to equal to 0 before, and you have all three options to choose from. You can do factoring, you can do completing the square, and you can do the quadratic formula. It is up to you. So as I do this, I end up with 2y squared plus 8y, and then I would get 10 minus 4 gives me 6. Now, if we remember our golden rule of factoring, the GCF, if I want to go ahead and do factoring, I'm going to take out this 2, make it simpler. So I have 2 times y squared plus 4y plus 3. And I can go ahead and get rid of that and divide each side by 2. So now y squared plus 4y 3 equals 0. And then I can factor. So I have y factors of 3 that add up to 4 are 3 and 1. So y is going to equal -3, and y is going to equal -1. That right there shows me I have 2 points. So I need to find my x's. So I can plug, now I could plug back into the circle, but I can plug right back in here. So I'm kind of moving all over the place. I have when y equals -3, again, I'm trying to organize my work. X equals -3 plus 3, which equals 0. And when y equals -1, x equals negative plus 3. So I get 2. So my solutions, you're not always going to just get 2 solutions, but for these 2 examples we did. We're going to get the point 0, -3, because again, x, y, and 2, -1. To see what that looks like on a graph, here's that beautiful circle we talked about before, 2 units to the right, 3 units down. Here's that center, radius of 2. Here's that beautiful circle. And then our line that intersects it is at the point 0, -3, and 2, -1. I always like to see the graph as confirmation to make sure what I did was correct. Using Desmos, it's going to be a great tool here for you to confirm your answers if you'd like. All right, last example. It doesn't happen often, but it can happen where when you're doing 2 nonlinear equations, so if you're having 2 circles or 2 parabolas, you can solve by elimination because your variables are the same. If we look here, I have x squared, y squared, and then equal to constant. So I can go ahead and eliminate. These are not those steps. I should have deleted that out. Sorry about that. That would be to substitute. So if we go ahead, you can just multiply this either by -4 or multiply by -1 to get rid of our y squared. So let's go ahead and do that. So I get 4x squared plus y squared equals 13. And then I have -x squared, -y squared equaling 10. Sorry, -10 because I almost forgot to distribute the negative. Now I can add my equations together like I do with elimination. My x squareds become 3x squared. My y squareds cancel. 13 plus -10 gives me 3. Divide by 3. And I'm going to get x squared equals 1. And now remember, when you solve I take the square root of both sides, and when I take the square root, this will become plus or minus 1. So this is actually 2 answers for x. So I'm going to, when I plug back in, try for 1 and negative 1. So let's plug in when x equals positive 1. I'll use my second equation. It's the easiest one. Why not? So I get 1 plus y squared equals 10. Y squared equals 9. Ooh. Now, again, when I take the square root, I got y equals plus or minus 3. What does that mean? That means, so far as a solution, I have the point 1 and positive 3, 1 and negative 3. Because when I plugged in positive 1, I get plus or minus 3. So now let's evaluate when x is negative 1. And you might already know the answer because you know what happens when something gets squared. This becomes positive 1 again. So y squared equals 9. Take the square root. So y equals plus or minus 3. So again, that solution is going to be at negative 1, 3, negative 1, negative 3. Notice that showing your work, doing it in your head sometimes allows us to forget an example. And you might be looking at these and saying, these are 2 circles. How is it that I got 4 points? It's actually that this is what we call an ellipse, or you can think of like an oval, because this 4 is stretching that out. It's no longer a perfect circle because the coefficients aren't the same. So graphically, we can see here is that ellipse, that first equation in red, and our circle in blue, and here are those 4 points of intersection. I hope that this has been helpful. If you have an assignment on Delta Math, please reach out with any questions. Feel free to rewatch this video, and I hope everyone's doing well. Miss you all. I can't believe this weekend is Memorial Day. Hope everyone's doing good.